What is a limitation in today's communication? In traditional communication, every bit of data is transmitted, flooding the network with unnecessary traffic. Machines speak in data, humans speak in meaning. Semantic communication brings them together. Imagine a system where we transmit only what matters, the meaning, saving bandwidth and reducing traffic. This concept, called semantic communication, shifts the focus from raw bits to meaningful information. By concentrating on meaning, semantic communication reduces the amount of data that needs to be sent, which saves bandwidth and lowers network congestion. Now let us look about our overall architecture. Here we mainly focused on semantic feature extraction. Our major contributions are adaptive patching implementation, SwinJSCC encoder, and codebook. Let's dive deep into how we implement it. Initially, the source image is passed through the adaptive patching module. Let's take a closer look at the operations within the adaptive patching module. The adaptive patching module takes the original image as input, along with several parameters. Then it applies Gaussian blur to the image. Next, it performs canny edge detection to extract prominent edges. Next, the module performs quad-tree partitioning based on the edge detection results. In this process, the image is recursively divided into 4 quadrants. Regions with fewer detected edges below the specified threshold are assigned larger patches, while regions with more complex edge information are further subdivided into smaller patches. Since below 70% of the image pixels contain image contents, the adaptive patching status is set to true. The generated image patches are then arranged in a left to right, top to bottom order. Next, the patches are extracted from the original image according to the established order for further processing. Next, all the extracted patches are resized to a uniform patch size. As you can see, regions with higher content complexity contain a greater number of smaller patches, reflecting the adaptive nature of the partitioning process. Subsequently, all the resized patches are padded with a fixed padding size. All patch information, along with the resolutions of both the jumbled image and the original image, is written into a coordinate binary file, coord.bin. Finally, all the resized and padded patches are arranged to form a jumbled image. Then the module return, metadata binary file, adaptive patching status is true, and jumbled image. Let us see about when adaptive patching falls. This is the respective quad-tree partition image. Since the image details are distributed uniformly across the entire image, adaptive patching becomes inefficient. Here we will write only the original image resolution as the metadata into the coord.bin file. And here module will return metadata binary file, adaptive patching status is false, and an original image. Adaptive patching module outputs jumbled image and patch coordinates binary file. Then the jumbled image is sent to the SwinEncoder for feature extraction. Let's deep dive into the SwinEncoder architecture and mechanism. Here is the SwinEncoder architecture. Let's look how a shifted window transformer works. Images are first divided into smaller patches. Then a window-based self-attention mechanism is applied within each window, allowing the model to focus on relationships between patches in localized regions. This helps reduce computational complexity while still capturing important contextual information. Then the windows are shifted and the same window-based self-attention mechanism is applied again. This shifting allows the model to capture cross-window dependencies and enhance global feature representation. After that, the patches are merged to capture global relationships. Then semantic space latent binary is transmitted to codebook module. Let's dive into codebook operations. The codebook maps each row of the vector to indices before transmission, which significantly reduces the dimensions of the transmitting vector. As you can see, when we use a 4D codebook, the dimensionality is reduced by a factor of 4. At the receiver, the same codebook is used to map the received indices back to the corresponding rows to reconstruct the semantic feature vector before decoding. Codebook module outputs semantic latent space binary. Then both patch coordinates binary and semantic latent space binary merge into combined binary. Then this is transmitted via wireless channel. After the entire encoding process, we obtain a combined binary file.
The combined binary file is then modulated using a deep, learning-based autoencoder model. The encoded symbols are transmitted using the USRP N210 device. The symbols are transmitted over the wireless channel. On the receiver side, the RTLSDR captures the symbols transmitted over the air.
Now let's watch how the real-world transmission is done using our experimental setup. Here we are using USRP N210 as transmitter. Now you are seeing the MATLAB UI for transmitter along with the transmitting process. Up to this point, we have observed the transmission process. Simultaneously, it is essential to handle the reception of packets as well. Let's now take a closer look at how the receiving process is carried out.